Let us consider this simple elastic structure which has a movable clamp on the left end and has a roller on the right end which can move vertically. The straight trivial configuration of equilibrium is this, and this is an elastic beam. So we know that this structure has a critical load, is well known, is given by this formula. And here we have sketched the deformed configuration after buckling. This is a well-known example, but I would like to draw your attention on the effects of the curvature of this constraint on which the roller have to move, and in particular also on the shape of this constraint. So imagine that this constraint has a circular shape like this. So this roller has to move along this circular profile. What it happened is that the curvature strongly influences the critical load. Now we have two critical loads, one in compression, one in tension, so this structure has a tensile bifurcation. Moreover, the shape of the constraint strongly affects the post-critical behavior and the elastica. And in particular, we see that for this structure there is a tensile compressive transition. I mean, when I pull this rod in tension, it buckles, goes like this, the roller goes like this, and when it reaches the vertical position, then the force here has to vanish to maintain equilibrium, and after this point the force has to become compressive to maintain equilibrium. So from this example it is clear that the curvature and the shape of the constraint has a deep influence on the critical and post-critical behavior of this structure. Now we can consider simpler systems, 1 degrees of freedom structures like this, and we discover several new effects. For instance, this structure is made up of a rigid bar which is connected through an elastic hinge on the left and which can move, and so we can apply a load like this, and on the right this roller has to move along a circular profile. So we discover that for this structure we have only one buckling load, and it's a tensile bifurcation, it's a tensile load. But more interesting is this case where we have combined two circular profiles joined here. So here again the straight configuration is a trivial equilibrium configuration for this system, but if I pull this structure in tension it will buckle this way, and if I compress it it will be buckled this other way. So this structure, which has only 1 degree of freedom, has in fact two bifurcation loads, one in tension and another in compression. This thing is at the first glance very surprising. Moreover, we can design the shape of this constraint to obtain a shape like this, more or less, to get this structure, which again has a bifurcation in tension and compression, but the peculiarity is that this shape has been designed in a way that it gives rise to a neutral post-critical response. I mean, the curve is like this, the load is constant along the post-critical behavior. So we can play with these constraints to obtain very interesting effects. Now the question arises if all these structures are a curiosity or if they can realize in practice. Since if we can realize this structure in practice, we can think of exploiting them as simple mechanical systems to obtain certain effects. To give an answer to this question, we have to move to the lab, and we will see that the answer is positive. On my back you can see the experimental setup for testing elastic beams. So the elastic beam is made up with these two metal strips clamped on the top and having a roller on the bottom. The roller can slide along this S-shaped profile. It's hardly visible, but there is an accelerometer mounted on the top of the structure to detect the precise instant of bifurcation. And the vertical load is given through movement of the top of the frame and is measured through this loading cell and this other loading cell independently, and the movement of the top of the frame is measured internally to the machine and independently with this displacement transducer which have been added by us. So this is the experimental setup for the tests on the deformable structures. When we test the 1 degrees of freedom system, we have to replace these metal strips with a rigid arm, this one, which has a rotational spring on the top and can slide with the same roller on the S-shaped profile. And when we have to test the neutral post-critical behavior, we have to replace the S-shaped profile with this other profile, which has been specifically designed to obtain the neutral behavior. So let's look at the experiments now.